Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
Alright, now let's go ahead and do just a brief summary of everything that we've covered so far, just to tie everything back together. By the Arrhenius definitions, an acid is a substance that dissolves in water to produce H+, or the H3O hydronium ions, and a base dissolves in water to produce OH- ions. By another definition, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Any pair of molecules or ions that can be interconverted by transfer of a proton is called a conjugate acid-base pair. Now, neutralization of an acid by a base is a proton transfer reaction in which the acid is transformed into its conjugate base and the base is transformed into its conjugate acid. And the more stable charged species is the one in which the charge is more delocalized. The Bronsted-Lowry bases with two or more receptor sites, remember, will be protonated on the site that gives a more delocalized charge. Also, pi electrons can act as Bronsted-Lowry bases to give cations, a reaction that is important in the chemistry of alkenes that probably isn't covered in your course, but good to know anyway. Moving into acid dissociation constants, pKa's, and strengths of acids and bases. We know that strong acids and strong bases completely ionize in water, whereas weak acids and weak bases only partially ionize. We know that the acid dissociation constant, Ka, is a quantitative measure of acid strength, and acid strengths are generally reported as pKa values, which are opposite log of the Ka. And then also stronger acids have larger Ka values and therefore smaller pKa values. And the position of equilibrium in an acid-base reaction favors reaction of a stronger acid, so this is the one with a lower pKa value, with the stronger base to form the weaker acid, that with the higher pKa value, and the weaker base. The acidity of an acid is determined by the stability of the anion that's formed on deprotonation of that acid. And factors that influence the stability of this anion are electronegativity of the atom bearing the negative charge, because more electronegative atoms are more stable as anions. The size of the atom bearing the negative charge, because larger atoms can more easily accommodate a negative charge, so it's spread over a larger area. Delocalization of charge of the anion, usually described by resonance contributing structures, because greater delocalization of charge is stabilizing. The inductive effect, because adjacent electronegative atoms, such as the halogens, will stabilize a nearby negative charge. And hybridization of the atom bearing the negative charge, because the greater the percentage of S character, the more stable it will be as an anion. And then finally, the last thing that we covered was the definitions of Lewis acids and bases. Lewis acids being species that can accept pairs of electrons, and Lewis bases being those that can donate pairs of electrons. So all Bronsted-Lowry acids are also Lewis acids, and all Bronsted-Lowry bases are also Lewis bases. But the Lewis acid-base model is far more general in that it can apply to reactions beyond just proton transfers.